Yeah, welcome back, everyone. I'll just pick it up from where I stopped prior lunch. Quick recap: we were discussing about how we have been able to apply CT existing CT methods to test AI/ML models. We looked into correctness. We also looked into how CT can be used in generating explanations. Now, another critical component of AI evaluation is fairness, where we ensure to assess and make sure the model does not exhibit any discriminatory behavior. So we have applied CT to perform fairness evaluations on pre-trained machine learning models. Specifically, we explored how CT can be used to identify individual fairness that the model may accidentally exhibit. So here is a framework on the right where we given a data set, we create the process is same. We create an input parameter model based on the data set, generate abstract test cases, convert them to concrete test cases. Then in this framework, for each of the concrete test cases, we try to flip the protected attributes value and see how does the model exhibit a different behavior when we change from, let's say, from male to female, or when we change across ethnicities. So that's a very high level overview of the framework, how we went about it. Can we go to next slide, please?
Yeah, 1 second. I clicked something and I lost.
Wait,
I don't know. I clicked on the Zoom and it went to full screen and I don't know how to unfull screen on Windows.
F11.
Oh, we need the slides, right?
Yep. Yeah, this is good.
Okay.
I just won't.
If
I
you
won't.
click this window.
Yeah, I will not click that window ever again. Okay. All right, Jagan.
Yeah, sure. Thank you. So yeah, we tried exploring how CT can be useful in identifying fairness issues in pre-trained ML models. And you can see the results over here where we were able to identify quite a number of fairness issues exhibited by 4 different models trained on 3 different data sets. So this pilot study showed us CT can be used for identifying fairness issues in ML AI models. Next slide, please. So yeah, so till now, I was been talking about how CT can be used to test machine learning models. Given that CT is a black box approach, its applicability is not restricted only to machine learning applications. It can be applied to other AI systems as well. Recently, we have been exploring how we can use existing CT methods to test other AI systems. In this case, we have been exploring how can we use CT to test large language models. So this is from our recent work where we explore how to perform robustness assessments of large language models. So currently, evaluation of large language models are performed using variety of benchmarks. Benchmarks are nothing but a set of tests that's run on a model, and an evaluation is performed and to see how the model performs on a particular subject areas. A common practice is to probe the model's knowledge via question Q&A, to be more particular, to test the model's capabilities on certain subject areas. Multiple choice questions are provided to the model and its responses are assessed. In this example, you can see on the right, one of a test case is a combination of questions and a set of options. Here in this example, you probe if you're assume that you are testing the model's knowledge on geography. One question could be, what's the capital of Australia? And you can provide 4 options and see what the model respond back. The current practice is compile a list of questions like this, feed into the model, collects its responses, aggregates the results to see how well the model knows about it. However, there exists a problem such that what happens if there is a change to the way in which we are asking the question to the model? Meaning, what if we change the way, what if we replace some of the words from the question with its synonyms, or what if we remove some of the options, or we don't make any major structural changes to the question, rather just modify the options and modify the order in which the options is being provided to the questions. What I mean by that is, rather than providing 4 options, Canberra, Sydney, Melbourne, and Perth. What if we swap the options, order of the options, and see if the model response back continues to predict the same answer? Like, I intuitively will expect, irrespective whether Canberra appears on top or in the middle or at the bottom, the model should pick the right answer. But does the model continues to do that? So existing studies have shown that that's not the case. The LLM's prediction tends to change if there is a change in order in how the model is being provided the questions. So we want to perform robustness assessment to have a good confidence in system's ability. Ideally, we need to perform an exhaustive testing where we test all possible orderings of the multiple choice questions to see if the model continues to predict the same answer irrespective of the ordering of options. But performing an exhaustive testing is not possible, because in this example, we have a question with 4 options. We are looking at 24 questions in total to assess the model's robustness. So assuming you have a test set with 100 test cases, we are looking at 2400 test cases just to get a confidence how robust the model performance is. So as discussed in the morning, CT can be a good alternative as a pseudo-exhaustive testing technique. So we explored the applicability of CT for this problem. Can you go to next slide, please? In particular, we use the sequence covering array, which was presented earlier today, to generate additional test cases such that the ordering of the options are guaranteed. In this work, given a question, we generated additional test cases using the 3 sequence covering array, which guarantees that 3 of the 4 options all orderings of the 3 options are covered using the sequence covering array. So as you can see, on step 1, you take the question, we provide it to the sequence covering array. Using sequence covering array, in step 2, we generate additional 6 questions. So in total, we have 7 questions to assess the robustness compared to a 24 exhaustive test set. Next slide, please. Yeah, so we looked into the results. This is a pilot study. This work indicated the applicability of CT in the LLM space as well, where we were able to see, where you can see on the slides that in most cases, when we perform this robustness evaluation on GPT 3.5, we did tend to see the model tends to, we observed that model tends to perform or change its responses upon changing the order of options. And we were able to detect a significant number of robustness issues in GPT 3.5 with just additional 6 test cases. So this goes on to show that CT can be an effective testing technique to perform robustness assessment for LLMs. So, yeah, next slide, please. So yeah, to summarize, I presented a set of existing work from in this area where we were able to use existing CT techniques to test AML models. However, as you all know that testing model is one aspect of testing AML systems. Data plays a critical role, and to a larger extent, it influences the behavior of AML systems. So it becomes essential to validate or perform assurance of data that is used in AML systems as well. So to do that, I'll hand it over to Erin, who will go in detail about how the new methods and metrics of CT for testing AI, which focuses more on the data assurance aspect of testing AML systems.
Thank you, Jagan. So yeah, we've talked a little bit about testing the input space. We've talked a little bit about how we represent data for machine learning models as either tabular data sets, how we design an input parameter model. And now we're going to talk about what are the applications to thinking about data, where we can start to develop new CT approaches. So just to drive home that we really need data assurance in order to have AI assurance. This is because we want to have things like robustness to small changes in the input space, security against adversarial inputs, We want to be able to mitigate unintended data bias that can prevent representativeness or generalizability. And we ultimately want to have explainable performance, but one that is explainable within a well-defined operating environment. So we need to understand the input space that we are testing. We need ways to characterize that input space. We know that machine learning models are data dependent. So even if we have the same model architecture and hyperparameters, a change in the training data leads to a change, most likely, in the model performance. Often the prediction explanations are model centric. A lot of the approaches in the literature, like through LIME, and these do not tell you why, what is the cause of the challenge. For example, with the LIME tool, it can highlight the salient parts of an image, for example, that snow was leading to a particular prediction. But getting to the root cause, why is the model failing to accurately predict wolves instead of huskies in certain scenarios, required an analysis of the training data coverage, which is that it didn't have examples of huskies in the snow. And so the model was learning to associate wolves with snow. There's evidence of the black box transferability of adversarial samples, even across models with different architectures. So this is suggesting a data weakness, not a weakness in the learning algorithm. And then in computer vision domain, we can often think about metadata that capture contexts. So these are things like the look angle or the time of day or the resolution. And these contexts that are affiliated with particular samples capture conditions that could impact the appearance of objects. So you can imagine that the way a truck looks from profile is very different from the way a truck looks from overhead. And then when you start to get combinations of those things, you can really have changes in the way that the object appears. And if we only have certain contexts that are captured in the training data, we're only going to have model performance on those certain contexts. And so we really need a characterization of the input space. So we know models learn relationships between combinations of features and labels. And so how these interactions of features affect the probability of the label, and that these are necessarily complex. We talked about this morning. It's not usually a single feature. It's an interaction of features. And so we can't rely on one-dimensional statistics. When we have gaps in coverage in the training data, we can have a failure to model the relationship. And when we have gaps in coverage in the test data, we can have a failure to detect differences in model performance. And then last, this characterization can be applied either to the features in the engineered features or latent space features or metadata or both. And we'll talk a little bit about those different options. Okay, and then just broadly, we've thought about data coverage applications across the machine learning or AI lifecycle. So we can think about applying coverage to planned collection, planning to collect data that covers all of the contexts. We can think about within data preparation, what samples should we label? Should we start with samples that cover previously uncovered regions? How do we do data splitting? Instead of just randomly splitting, should we select specific things for the test data set so that we get coverage? Can we look into bias detection? Can we measure the coverage to detect when we have certain things that are overrepresented or underrepresented, or when a particular split has different bias than the original data set? Getting into model training, how can we think about reducing the training data sets if we design training data that covers the space? Does this give us similar performance to if we just have a very large number of training data samples? How do we think about targeted retraining? So if I find that I have a problem and I want to augment or fine tune my model, can I use coverage-based approaches to pick particular samples and do that retraining? How do we figure out which are the factors that are impacting model performance and then should be involved in coverage computations? We already had some examples, I think, of explainability for classifiers this morning. Then when we're getting into model testing, again, designing representative test sets, what does the coverage look like in my training data? And then how can I reflect that in my test data? Challenging test sets, what wasn't covered in my training data and how can I cover that in my test set? So I'm testing kind of new contexts. just black box covering test sets. If I don't know anything at all about the training data, what are the set of samples that I should probably include? Reduce test sets. Similar to training, if I have test sets that cover the space, can I get away with fewer samples? And then into deployment, can I determine which model I should use at a particular point in time? Can we think about weighting the votes across an ensemble? And can we think about out of domain detection if we have a good characterization of the input space? Okay, so a little bit of this is review. So data coverage metrics. The combinatorial coverage metric is fairly immediately adapted from combinatorial testing applied to software systems, but with the way of defining the space. So if I have U as a universe of, let's say, data columns and their sets of values, so U sub T is the set of all of the T-way interactions that are valid within that universe, then given a data set might look like the one up at this right-hand corner. So I've got these K data features that are the columns of the data, and then I have N samples in that data set. We can think about those two-way combinations of features and the two-way interactions that are present. So now I have this data set, D sub T is the set of two-way interactions that appear in that data set. Then the combinatorial coverage of the universe by that data set is defined here. It's the number of things that appear in the data set divided by the number of things that were valid for that universe with respect to that strength T. And then also, I've talked, I think, driven home that we have training data for ML models. And so how we think about what was present in the training data might be really important for trying to understand how different a test set is from that training data. And so we have this additional metric, set difference combinatorial coverage. And what that is measuring is the proportion of T-way interactions that are present in one set that are not present in a second set. So what's in T that's not in S, that proportion. And so when we start looking at these set relationships, this first example, we have an example of when we're measuring V minus T. So what's in V that's not in T? When V is fully subsumed by T in terms of its interactions, then we get this value 0. But if we flip the direction that we're computing that metric, so now we're asking, well, what's in T that's not in V? When V was fully subsumed in T, it was a proper subset, we get a value that is between 0 and 1. And I'm not going to walk through each one of these relationships, but when you compute this metric bidirectionally, you can end up pinpointing the exact relationship you are in. And so you have some sense of relationship between these two data sets. And these data sets could be, as I just described, the test data set and the training data set, but they could also be a data set for your original domain and a data set for a new deployment domain. So we could also kind of think about how far we need that model to transfer. And so getting into this idea of measuring the operating envelope in machine learning, a question we might ask is, can we transfer a model from one domain to another? And so we had a scenario where a model that was trained on southern imagery exhibited a performance drop on northern imagery. But when we trained in the north and tried to transfer it to the south without doing any fine tuning, we did not have that drop. So we could say that the north to south transferability was much better than the south to north transferability. And what did we find by looking at our coverage metrics? We found that the north covered more of the context of the universe than the south. It covered 93% instead of 83%, which is what the south covered. We also found that the north covered more of the south. It covered 98% of the contexts or the T-way interactions that were in the south than the south covered in the north. It only covered 88%. I should also note that the south data had twice as many samples as the north data. So the north had better coverage even with half the data. So we could conclude that these kind of measures might be quite useful for measuring the operating envelope of a model. We can also think about coverage as a basis for systematic training and testing. So the question might be, how do we differentiate a model's ability to perform in regions where it should have learned from its ability to generalize to new regions? And so in this research, we used factors from an autoencoder, and we tested the accuracy on rotated digits of a model that was trained only on non-rotated digits. So that was the rotation was a non-latent space feature. And then we also had latent space features. Okay. And so we have this model that's been trained only on these non-rotated digits. And then we had multiple test data sets or test samples. And then what we found was that the test samples that had all of their interactions covered by the training data set had higher accuracy than samples that had some interactions that were not covered. So we can think about these test samples being the interactions being fully covered by the training data set, those test samples as creating a representative test set. And then the collection of samples that had some interactions that were not covered by the training data set could comprise this challenging test set. How does the model perform when we give it new kinds of things it hasn't seen before? We can also think about reducing that gap in transfer learning. So I've got a model, I've got it trained one place. I try to see if I can deploy it to some new domain, and I have some reduction in performance. And so now I need to try to improve it so that I can send it out for that new deployment. So we want to know what are the top information gain data points that can be used to improve that model. And so what we found was that when we retrained the source model with images from the target domain that were selected by that set difference combinatorial coverage metric, we got higher accuracy than when we retrained on the same number of images that were randomly selected from the target domain. So in other words, using this sense of gaps in coverage, go get samples from that gap, we improved the performance more than just the same number of samples. So more data, not necessarily better data, better. Okay. Another question, what are the critical metadata for operating envelopes? What are the dimensions of the operating envelope? Can we know in advance when we're leaving it? So this work used a data splitting algorithm and a systematic inclusion-exclusion framework in order to identify the critical metadata that impacted object detection models. So what we did was we went through and we systematically withheld some interactions from training in order to create a training data set that had a intentional gap. And we did this for each one of the interactions of interest. So you can think of like training data set A was missing interaction A, model A is tested without seeing interaction A, B, C, D. So we've got this kind of constellation of models. And then we also had a universal test set that covered all of those interactions. And so then for each model, we evaluated that model on the universal test set partitioned into either the covered portion or the uncovered portion. So for example, model A would be tested on interactions that contain that withheld interaction A as the uncovered test set, and then also on all of the other interactions that were seen in training. And then we compared the deltas. We tried to see when does the model have different performance on the uncovered versus the covered partitions. And so here you can kind of see that in the left plot, when we're looking at top is precision, middle is recall, and bottom is F1. So some performance measures that are appropriate for computer vision. There was a difference in performance on the covered data set versus the uncovered data set. Particularly, there was a really wide range over the uncovered data sets. And then when we looked at the particular factors, we found that for some factors, there was in model performance between those sets, and for some there weren't. So here, I think I'm showing precision, but average pan resolution, biome, and hour of day for precision, that middle, there's a difference in the performance, whereas for off nadir max and season, there's not so much of a difference. So we would conclude that the metadata features average pan resolution, biome, and hour of day are impactful to the model. If it doesn't see them in training, it's not going to perform well in deployment or in test, whereas off nadir max and season might not be impactful for precision. Okay. Up until now, we've been mostly talking about coverage as a binary thing. It is either seen or it is not seen. It is present or it is not present. And this works fine for software. With machine learning, when we have this element of statistical learning, it is it is the case that as we go through learning, the more times you see something in training, it reinforces those weights. And so if something is seen once in the training data set, the model may not adequately learn about that feature or interaction of features. Whereas if it's seen many, many times, it may be learned. So one of the research questions here was, does frequency coverage correlate with model performance? Are things that are more frequently covered in training, do they have better performance? And also, can we detect data bias that might lead to differential performance prior to training? And so in this work, we did not manipulate the frequency of the data. We just had two different data sets, one that was balanced and one that was unbiased. Everything appeared more or less the same number of times, and then something that was heavily biased. And what we found was that the more biased data set resulted in a lower performing model overall. So even overrepresented things had worse performance. And there was some correlation between the frequency, coverage, and performance, especially for the more biased data set. Once we got into more balance, we didn't see so much of a correlation. An open question is, what is the threshold for frequency coverage where the correlation breaks? And so more data no longer results in better performance. This is something we're thinking about. All right. I think we have about 2 to 3 more slides in this section, and then we're going to move ahead to the looking forward. So again, thinking about frequency coverage, this is actually an error. So in this case, this was the diabetes data set instead of facial recognition. But how do we determine the impact of data imbalance on model performance? So which feature combinations are most sensitive to data imbalance? And can we mitigate data imbalance impact through data volume? And so here, what we did is we came up with several data sets that had varying degrees of bias. And so the baseline data set was drawn from the original distribution. It had whatever bias was present there. The low bias, do we need?
I'm just going to grab this.
Okay. The low bias data set was designed to be as balanced as possible. So each interaction appeared with approximately the same frequency. Let me jump to high. The high biased data set had the most frequently appearing interaction for a particular combination driven way up. So it was appearing about 90%. 90% of the samples had that interaction, and the rest of the interactions were spread across the remaining about 10%. And then the moderate bias data set was halfway between balance and this high skew. And so then we took these different data sets, we built models, and we looked for impact. So when there was a large 10% or greater, or a 0.1 change in the performance metric, for example, a precision score that jumps from 0.8 to 0.9 would be something that we would count as being impacted. And then we looked, so that would be between low, moderate, or high bias. And we called something like a positive direction, or an R plus if we're looking at recall, when the model performance increases with skew. We called it a negative if it decreased with skew, and a nonlinear if it, for example, had the best performance for the moderate data set, but lower performance for low and high, or the inverse of that. And so then we looked at each combination that we were skewing on, and we looked to see how many of the models that we trained across 5 different algorithms were impacted for that combination. And so just to jump to the chase, we found that most combinations, skew in most combinations resulted in an impact in performance, and most algorithms were impacted by skew. And this impact did not correlate with the things that we thought it would. For example, we thought that skew in features that were deemed to be important by the SHAP feature importance method, and or involved the label, that these would be more impacted, and they were not. And additionally, we found that for the larger data sets, while there was some correlation to data set size and impact, meaning the more data, the larger sized training data sets had less impact, it was not a very clear correlation. And so this is just saying we've developed some methods for looking at frequency, coverage, and that we now have more questions, I think, than we originally started with. Okay. And then the last metric is the combinatorial frequency difference. And so here, this was alluded to in the morning, but it's looking at the difference in the frequency of value combinations in a class versus a non-class. So looking at the FC as the fraction of rows with a combination in the class versus the fraction of rows in the non-class. And so as an example, if combination X is in 70% of the rows of the class and 30% of rows of the non-class, then that frequency difference was 0.4. And this was used to analyze the susceptibility of physical and clonable functions to machine learning attacks. So it's used to identify bit combinations that have a disproportionately strong influence on the puff response bit values. Okay. And then I'm just going to round us out. A really important question is, okay, how do we use combinatorial testing and how do we use it in broader system test? So here on this kind of like VTP model, in this paper, we were looking at some post-deployment test for, this was cyber-physical systems, multi-agent systems of satellites. But what's really important here is that we have the systems V. We know that we create tests as we move down the left-hand side and we execute tests as we come up the right-hand side. And so we were trying to think about what tests should you use when, given what system, and how do you come up with a test plan? And so our flow through is to start out with the phase of test. Where are we in the VTP model? To think about the field of study. So a teeny of a composed system needs to draw from scientific testing techniques for each subsystem, and therefore consider testing specifics for AI, as well as testing specifics for deterministic software, electronic hardware, and mechanical systems. We also need to think about the hierarchy of test. So the decomposition of a subsystem forms its own V model. So in a software module, a unit might be a function, while integration is testing the interfaces between functions. Whereas when we're at a different hierarchy of test, we might have a software package as a unit and then its integration with other software packages, or we have in a higher hierarchy, we would have all of the software and its integration with the physical hardware of the system. Test plan efficiency, we can think about the different test strategies or designs have different numbers of test points. So we've talked a lot about how covering arrays have fewer test points than full factorial designs. And those who are familiar know that fractional factorial designs have a fraction of the test points of full factorial designs. And we have different budgets at different phases of test. So for example, when we're testing the AI component in simulation, we can afford many more test points versus when we're testing the fully developed satellite in space. Or you can, other examples are if we're testing an autonomous plane flying, very different than in simulation. And so that's this kind of left-hand side that we can have increasing fidelity as we move up from digital simulation to deployment, but we have decreasing test points as we move that same direction. And then the test plan efficiency guides the focus of the test, given the cost of each test run at the current scale, and assumes system lower in the hierarchy function as expected. And then we think about goals of the test. So what do we need to know about it? Is it reliability, robustness, performance, bias, fairness, whether it achieves mission accomplishment, or if we're just trying to find, as many bugs as possible. And then finally, all of this collected knowledge through all of these steps guides the creation of the test plan, which tells us the specific tests to run. And so we might think about using combinatorial interaction testing or combinatorial testing at certain points in this overall test plan, given all of those kind of considerations. What is it that we're testing? Are we testing software? Are we testing AI? Are we testing the cyber physical system as a whole? Where are we in the hierarchy? And how many points can we afford? And also, again, what is the goal of the test? Do we just need to find faults, or do we need to be able to attribute variance to specific factors? That generally doesn't work very well with combinatorial testing. Okay. Future research directions. So we have started on this work, but there are many new questions. So one, human machine teaming coverage. Can we apply combinatorial testing to coverage of human operator characteristics, things like level of experience, role, maybe location, things like that? Can we apply coverage to human in the loop architecture? So where is the human interacting with the system? Are they just observing and they're going to hit a button if they need to take over for the system? Are they being involved in making decisions? Are they labeling samples? And then additionally, how do we use designs with non-discretized factors, for example, space filling designs, in conjunction with or instead of combinatorial testing? So as an example, for Bayesian optimization, there's a challenge. Bayesian optimization works really well when you have continuous variables. It doesn't work well when you have categorical variables. When you have categorical variables, you want to use like a multi-armed bandit kind of approach. And researchers have then married this Bayesian optimization with multi-bandit approaches to come up with multi-armed bandit. So where in that scenario, given the categorical variable that you need to set, you pick one of the arms and then you move into that arm, and that's where the Bayesian optimization is applied to the continuous variables. Could we do something like this and marry design of experiments approaches like space filling designs with combinatorial testing approaches? We don't know. I think we should try. And then getting into how can we use AI to help with combinatorial testing. Something we could try is coming up with this input parameter model. Right now, input parameter models are specified by SMEs, and it is a obstacle or a barrier to applying combinatorial testing. But we could think about using LLMs to come up with category partitioning. In other words, read the specification and derive bins, or identify constraints, or identify the various factors. We could also think about using LLM-based approaches to determine the best test generation algorithm. We think it's unlikely to be effective at actually generating the covering arrays because LLMs don't math well, but maybe they could act as a SME to know the literature and say, given the parameters that we've identified, you want to use this construction from covering perfect hash families. Okay, and then last, more work on combinatorial testing for AI. So there's work to be done on the test generation algorithms. The covering array algorithms assume that we can write down tests from scratch. So this is not applicable to the way data is generally collected, where it's collected in advance. And often we are trying to subset or select the data set samples from the data set samples that we've already collected. We need different algorithms to do this kind of a search for subsetting. For input parameter modeling best practices, how to discretize truly continuous variables when there's no natural cutoffs is an unsolved problem. WECA uses statistically but unintelligent approaches in terms of the knowledge from the specification. They may not be semantically meaningful, so they might not know, for example, that dusk and dawn are good times or good breaking points to break up the time of day. And so using physics-based approaches to come up with meaningful bins. Another open question is, do we include all the important factors? Our systematic inclusion-exclusion approach down selects, but it might not detect when we miss something. And okay, and then last, we've talked about these new coverage metrics. So previous approaches were binary. We're starting to work on frequency coverage metrics, but we need to do more to compare distributions. And we also don't know how much redundancy we need. For software testing, you see it once, it causes the fault, that's it. For machine learning, again, we might need to see the same interaction repeatedly in tests to determine that it is actually a problem. We don't know how how much we need to see that. Okay, so we're going to now jump into our hands-on portion. I don't know that I have slides for the ACTS.
Just,
You guys are gonna plug in?
I'm going to
He's
share.
gonna share his screen. I just made him a co-host, just because sorting out the computers again probably
Yep, agreed.
takes some time.
Okay, do I need to do something on my
Yes.
side?
So if you
Stop sharing.
stop sharing.
I'm gonna let you do that.
You should plug in here, right?
Do I need to plug in or you keep running? You just stop sharing your slide. That's it.
Yeah. But then everyone should see what you're doing.
I'm gonna
So
share.
On here, yes.
Yeah.
Perfect. Oh, let's see. Wait, this is not the right one.
No, I can invite share now.
Is this it?
Oh, so the problem will be this one is only getting input from here.
Yeah, I'll bring up the rest, your shared screen up here.
Okay.
I just pulled the wrong one.
So what I'm trying to do is I'm trying to share only the ACTS window as opposed to sharing everything else. And the idea here is that ACTS is the covering array generating tool. And this is just a jar file. If you have a JRE, if you have a Java runtime environment in your laptop, and you just run it and you get this window. So that's because I wanted to just share only this window. I didn't share the whole screen and double clicked on that. I just assumed that go ahead and run this window, the ACTS jar file, which you have downloaded. And we just want to show you, remember that screen that I had shown at the beginning of the day where we had these 10 different font scenarios like strike through and other different aspects. And what we have done is we had said, okay, does anyone remember how many variables we had? 10. And if we were to do all 10 possible combinations, all of them was binary. So 2 to the power 10, 1024. But then we said, okay, we don't want to do 2 to the power 10, 1024. We just want to do every three-way, right? And every three-way, I gave you a number, which was that 10 choose 3, 120, meaning there are 3 different variables that you can pick out of those 10. You can choose them in 10 choose 3 different ways. And then because they were all binary variables, each of those 3 would have 8 possible value combinations, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1. So what we're going to do, it's a pretty simple scenario how it does the covering array is that if we go ahead and if we say that I'm going to just create a new system, let's say we're just going to say font test. Okay. And then let's say some of the parameter values, I just noted it down to remind ourselves is that what were some of the different parameter values that was there. For example, there was one font scenario which was strike through. And instead of actually calling it the whole thing, this is just a parameter name. We don't care about it that much. Maybe I'll just go for a smaller name like str. It's a Boolean type of parameter. Now, ACTS allows you to actually choose multiple values, but I'm showing the Boolean one first because it's just simple. It's easy to follow the scenarios. And so what you are going to do is we're going to add this variable to the table. You will see that it has gone to the right. So str is the parameter name, strike through. And then the second one was double strike through. Now, I'm assuming someone is going to pretty soon say, wait a second, you cannot have strike through and double strike through at the same time. You know, it's not, or just a very similar way. You're not cannot have both superscript and subscript at the same time, right? So we're going to come to that issue. But first, assume in some magical way you could have both, and you could just try to see what would the font look like if you had both strike through and double strike through. And if that is a test scenario you wanted to generate, I'm just going to try to show you first how you're going to generate that test scenario, then answer the question. Some of these test scenarios don't make sense. Like, you know, you cannot have both superscript and subscript at the same time. That won't work. Well, you could still try to put it in the test case and expect that, no, I cannot do it. You know, some sort of error message or some sort of meaningful message. But assuming that in some mechanism, all of these things, combinations are feasible. All of these combinations actually make sense. How do I go about creating that? Okay, double strike through. That's my second parameter. Superscript, SUP. My third parameter, because these are Boolean, I'm not giving them other values. I'm just giving them true, false values. And these are, and then subscript, SUB as opposed to SUP. And then there was a shadow. There was an emboss. There was an engrave. There was a small caps. There was an all caps. And of course, someone's going to tell me, wait a second, that also doesn't make sense. You cannot have both small caps and all caps at the same time, right? But again, and there was a hidden. So I am just going with that whole screen that I had shown you, because you can go back to the slides and you can check. This is exactly what I showed you as the example on the morning. And if we were to go and do three-way combinations, we could just go ahead, add this system. So now we have the system. It has 10 parameters. Each parameter has binary values. And of course, there were other types of values we could have chosen, but here we have taken only binary values. And then we can go and we can say that I want the covering array of a particular strength. And we're going to build that covering array. And we have to say what kind of strength do we want? Do we want a two-way? Do we want a three-way interactions? Do we want a four-way interactions? And let's start with the simplest one. And the algorithm that we're going to use is IPOG. This is a pretty efficient algorithm. Does anyone remember the number of test cases I said that you will be able to cover all two-way in the morning slide? Just
the 34?
No, the when you get the covering array, that will have all two-way combinations instead of the 960 test cases. 13, right? And I said that if we are lucky, the algorithm will actually get us something that is even one less. Let's see what we get. It got actually even better. So it actually got them in 10. Right? So the algorithm in some cases would do a scenarios where it will go all two ways and find this. Now, if I wanted to just sort of say, okay, no, I want to see what will happen if I want to generate all three-way. So now we are saying that I want to get all three-way combinations. Now, this is two-way, that's why 10. The three-way is what we were trying to get to the 13, right? Remember so I scratched that. Well, that actually takes more. Well, this one, the two-way one was the possible ones that you could get, but it is one thing that I wanted to demonstrate that it is not necessarily always going to give you the optimal one. It's going to give you one of the optimal one that's pretty close, all right? And it's not going to necessarily give you the most optimal one all the times, but it is pretty efficient. The IPOG is pretty efficient. One of the things that I want you to actually now ask yourselves, what happens when I start putting on those constraints? Remember the constraints we were talking about? What if you have superscript, you should not have subscript. If you have strike through, you should not have double strike through and things like that. So what I can try to do is I can take this and I can try to modify this. And then I can say, okay, these are the values that I have. And I can add some constraints to this thing. So for example, I can say that if you have strike through to be true, meaning when the value of the parameter str is 1, the value of the parameter double str should not be 1. All right. So if str, that should imply, that's the right arrow kind of thing to say imply, you are saying not double str. So what you are saying is that if you ever see strike through to be true, don't make double strike through to be true as well in my test case. And if there is a test case, I don't want that test scenario. That test scenario doesn't make sense. Similarly, I could say that if you see a superscript, that would imply that you should not have a subscript. So if you have a font that you are actually trying to see if it can do the superscript properly or not, you should not be in the same test case also make the subscript to be 1 as well. So I'm adding another constraint that, okay, superscript, having superscript implies that subscript will not be there in that same test case. All right. So I just added, for the sake of this demo, 2 constraints, and then I modify the system, and then this will clean the existing covering array that it has, because the covering array is going to change now. So we're going to go and try to build this system. And let's say we're going to build it with these constraints. Luckily, it was able to do the same number of things, but hopefully it has managed to get those constraints in place. So in other words, if you look at the first 2 columns, you will not see both of them true anymore. So in this particular case, it was able to accommodate the constraint without having to increase the number of test cases. Remember, it always looks for the optimum number of test cases to accommodate not only all the combinations, but also to accommodate the constraint. In this particular case, it happened to be able to accommodate that without increasing. Sometimes it will. Yes?
It can also decrease, right?
It can also decrease. It can also decrease. A lot of the times it can decrease if it needs to not have a particular test case where that particular scenario is there. But the idea that I'm trying to get across is that it will always try to come up with a very compact test cases, a set of test cases. So the similar thing you will see between the superscript and subscript because we just added those two. And that one will not have these other scenarios. What I would like you to do is just show you that if you wanted to add some other kind of scenario, let's say I wanted to add that, okay, I wanted to see it's not only doing it for all these different Boolean variables, how about a non-Boolean variable? Like, for example, let's say font type or font, and let's say we're going to make it an enumerated one. So for example, we're going to say that Times New Roman, Arial, Calibri. So just adding three, in addition to those 10 variables, 10 Boolean variables, now I'm just saying that in addition to that, I'm going to have also the type of font. So the test cases, each row of that is not only specifying what font decoration you are putting in place, it is also saying what font it is. Similarly, we could even add the size, right? And then we could now say, okay, go ahead, modify the system. First of all, I need to add this new item. Now, what I would like you to notice is that this new item is no longer just a true false. It is an enumerated values. It has 3 values here. It could have 5, 6, 7 different values. Similarly, I could have a font size and I could choose certain fonts. Now, this is where the art of the input modeling will come in, because you definitely probably don't want to design your test suite where you are going to have font size 1, 2, 3, 4, 5, 6 all the way to 100. Rather, you would probably choose certain sectors of fonts, like you may want to have a very small font, like a 1 or 2, a reasonable font that gets used a lot, 10, 11, 12, maybe 1 large or 2, 3, 4 larges, 24, 48, one of those numbers. So selecting those values is the art part of this designing the input space. So now what we can do is we can modify this system. It's going to wipe out the previous covering array because that doesn't make sense anymore with this new system. And then we can try to build it. Of course, the 2-way or 3-way strength. And we can go ahead, and this has given me 26 values. Now, remember that logarithmic thing that I was talking about, that it grows pretty slowly? I just added one more parameter, and with 3 different values. And I haven't gone up that much, right? So, and I could actually show it if I added a number of more parameters. The number of test cases needed for all 3-way interactions is not going to grow that fast. It's logarithmic to the number of parameters that we have. So in this particular case, you will see that in addition to all the different binary parameter values, this enumerated one is over here. Now, you can download it, take 1 row of it, and design your test case out of 1 row. Take another one, second row, design your second test case using those values, and so on. So that is sort of the basic of it. And then this is just the start point. And then you can just take it and use it. We have used it into test generation process, so where the generation of the covering array is just 1 step. And then you can take those values to help you actually transform it to the proper input set that is needed for your particular application. And you can automate that or make it manual and have that scenario work out. Questions, comments so far? This is the base case. This is the basic ACTS. Yes.
It's using the same algorithm to calculate the size.
I chose the same algorithm, the IPOG, that was developed by our colleagues at UT Dallas.
What's the difference between algorithms?
So we recommend the IPOG because what we have found that has consistently given us the most efficient, because what we are after is the most compact covering array, and also the one that runs faster. Now, these are values that you have seen have been computed pretty quickly. But when you are talking about 50, 100 different parameters and many different values, things slow down a little bit. And having the more efficient algorithm is very useful in that case. So our experience has shown that the IPOG one is pretty efficient, relatively speaking, and we haven't had a scenario where generating the covering array was the bottleneck. We haven't dealt with that large of systems, maybe. Yes.
Can I add that when you're thinking about really, really large systems, there are better algorithms, but there are not tools that can help you construct them.
So one of the things is we have this international conference on combinatorial testing, IWCT. Rick, Raghu, they had started it, and many algorithms also have been over the years been proposed and shown over there. So this is not necessarily the optimal algorithm. There are algorithms that have been developed, but this is the one that is available in our tool. By the way, you saw that there are a few other algorithms implemented there. So you are more than welcome, and we will encourage you to actually try other algorithms if you have large parameter set and large parameter value space, and give us the feedback whether if in particular scenarios, if another algorithm worked a little better than this one.
This one is particularly good with constraints also. Some of the others, you can possibly generate smaller arrays, but that tends to be in the case where they don't have constraints. But you've almost always got constraints, so that's a very useful practical factor.
And some of the other algorithms also slow down significantly with the constraints. So this was kind of the best of both worlds in terms of the efficiency and in terms of the handling the number of parameters. So this is the basic covering array generation tool. We have, I mean, so we Rick writes a bunch of code, and we write some code to put together to develop some research prototype. So we always have these research prototypes in place. For example, the line graph that was showing that what percentage of your data have two-way coverage, 100%, 50%, 75%, and what is not covered. That line graph there is also a tool, we call it the Combinatorial Coverage Measurement, CCM tool. And then finally, all these matrix, the new matrix that we were showing, like what combinations are present in one class and not present in another class. But more importantly, when it comes to machine learning algorithms, we think about it is not only what combinations values are present in a particular data set. And let's say you have a machine learning data set, and then let's say it is doing some sort of binary classification, like, is it reptile or is it not a reptile? And based on some characteristics, does it have wings? Does it have skin? Does it have fur? Does it have how many legs does it have? And things like that. Let's say you have a bunch of those features, and based on those features, it is giving you classification of whether it is a reptile or not a reptile. Now, what you want to sometime analyze is that not only what combinations of values are present in one class and absent in another class, also how frequently some combinations are present. What is the frequency? So we have another tool called the combination frequency differencing. And there are some papers that Erin was mentioning about analyzing your machine learning models data based on what frequency of, how frequently certain combinations were present. So we have another tool that we have made available for today's short course called this combination CFD, we call it for short, combination frequency difference or combinatorial frequency difference. And what we have, I'm going to stop sharing this one. And I'm going to share another window of running. So this is another just if you it's just a Python code, and we had one of our summer students have been developing the GUI version of this Python code. So instead of showing you the whole, I can try to see if I can show the whole screen, but if I share the whole screen, it's going to share also the Zoom. So that's why I'm sharing not the whole screen, just the. Okay, so this is what I'm going to do. So if you just have your. So if you download our CFD tool, you will see that this has a Python code, and you can simply just run. I don't know whether it will. So the CFD research prototype, the combinatorial frequency difference, if I run it, it's going to come up on my window, but it's not going to come up on your window. So I need to stop sharing that window and share this. So what I just did is I just ran the Python code of the combinatorial frequency difference. This one. Okay. So the purpose of this tool, very simple, is that it goes on and it asks for two classes of data. If you have a machine learning model that you have fed in a bunch of data and it has produced two classes of classification of output, let's say you get those output. For example, you gave a bunch of feature descriptions of whether a particular animal had how many legs does it have, whether it has fur, whether it has wings and things like that. And it is doing some sort of classification, whether it's a reptile or not. That we're sticking to that example because that was the example we used in the morning slides when we were describing how this could be useful. So one thing that you can do is you can go ahead and in this GUI tool, you can just upload the class file. So we can upload this reptile file. It's basically file with feature values, just 0, 1, 0, 1, and in some cases, whether it has wings or not, whether it has feathers or not, whether it has fur or not. So some binary values, and in some cases, some non-binary values, like how many legs does the animal have. So this is what the class file reptile basically has all the values that was classified as reptile. In other words, these are one classification, and then non-reptiles are animals that have characteristics and have been classified as not a reptile. Now, you may be asking the question that how did it come up with the classification? And to do that analysis, so this is sort of looking at the training data set and trying to understand what is the characteristics of the training data set from the lens of the combinatorial, the combinations of values present in one class versus another in terms of how frequently certain combinations are present in one versus another, whether there are some unique ones or not. So you can say that I want to see if there are combinations of values, two-way combinations of values or three-way combinations of values that are 5 times more frequent in one class compared to the other class. So that's the 5 cutoff point. And we can try to ask it, okay, now calculate the combinations. And this one is just going, and this is a Python code that would go ahead and try to come up with. It's updating the screen. So it's going to give you some information what we were showing as to the combinations that are present. For example, you can see that there are some things which are unique to the non-class, meaning the not reptile class. Here, class and non-class are basically, we are just labeling one of the data sets as the class file, one of the data sets as the non-class file. You can think about it as like if you were given a bunch of image and asking the question, is it a cat or not? And the ones that it answered, yes, it is a cat, that was the class file. And then it's not a cat, that was the not class file. So similar scenario is the one that is, it is a reptile, that was the class file, and is the not reptile are the non-class file. So he is saying that there are some scenarios in this particular data set. This is a toy data set. It's not a real, this is a toy data set. And what you can see is that what are some of the unique features that are available in only the non-class, and what are the combinations of features that are available in class versus non-class. So what you are seeing is that what is available in the non-class and what is available in the class in terms of the two-way and three-way. It's going to run out of space, but I'm going to just try to show you that you could go and try to see the three-way combinations as well. And I'm just going to switch up the three-way combination for now. And I chose the verbose output to show this scenario as to how many of these are available. Now, this has a bunch of, so this is a tool that would give you some sense of what your data characteristics look like. So it's going to tell you like how many values you have. And as I said, this is a toy example. So there were only 5 samples in the class rows. There's 5 rows in the class file, 96 rows in the non-class file. And then you can try to ask the question that if there were certain combinations which were present 5 times more frequently than the other ones, consider them to be notable value combination, NVC, notable, I'm pronouncing it wrong, notable value combination. So that is the NVC. And there's notable combinations, how many of them are present, it's going to tell you that. And then it can also show you all those values that you have that are notable and to what frequency do you have them available. There are some, by the way, this is, as I said, it's a research prototype. It's being developed even now. There are features getting added. The student is working on it even now. So there are some, not this one. So let's say you wanted to select some variables and wanted to see interactions of that variables. You can generate the combinations of them, one-way, two-way, three-way combinations of those present in the data. But this is probably not the most useful. Let me show you another one. Remember the Venn diagrams that we were showing you? That this is the more useful piece of understanding. So what combinations of values are present in the class and what combinations of values are not present in the class, or how frequently certain combinations are present in the class and not present in the class. Those are all there, okay? So that is the usefulness of these tools, but the tool that we use the most is the ACTS, and we do analysis of this one. And there are some other graphs that we can generate, for example, with frequency difference, which we have not shown in today's assignment. But then the major thing that we would like you to actually walk through with us is the Codex tool. So we're going to move on to the Codex tool, and Brian is going to actually walk you through that one.
And I think given what time we're at right now, I think if we take our break right now, then Brian can take us from 3 to, and then we're gonna end at 4:30.
Sounds good.
All right, so we're gonna get into this, just a little walkthrough of codecs, something that we've been working on for a while. And we're excited to share with you. So thanks for sticking with us. Now it's been a long day, so yeah. So with all this in mind about data assurance and characterizing your input space and all that, we thought it would be handy to have a tool which we are calling Coverage of Data Explorer, or Codex for short, to kind of implement these coverage metrics so that you can apply these on your custom data sets just with some input materials provided. So what this tool entails and what it's supposed to get at with your experimentation is to enable dynamic decision-making on various partitions that you have of your data. So you can visualize them and interactively train machine learning model envelope and in an iterative process. And then also to understand, I guess, a sufficient amount of training data, training or test data that is needed for your machine learning models. And then also what factors define your operating envelope that make up your data set that might impact your model performance. And then just other various functionalities, modes of analysis that involve combinatorial coverage or set difference combinatorial coverage for your results. Yeah, so with this walkthrough, I'll be happy to have a demonstration of how one would use this to test your own data sets on. So we just prepared some learning objectives for you so you kind of know where this is going. So firstly, we're going to get at how to even install Codex and its dependencies. And so what we provided on the NIST site was that codex.zip. If you're following along, feel free to pull up something like this, like your file browser that has your codex.zip. And then you'll also need some kind of command line interface, whether that's you're on Mac, you can use your terminal, or if you're on Windows, you can use your command prompt, or PowerShell looks like it works better. And I gave you some time to install Python 3.10 or newer. If you haven't, just do so now and just follow along. And any text editor might be good because you'll get a chance to interact with some of the input materials hands-on. So just if you're not familiar with the command line, just some basics so that you're not completely lost would be, the first one is to cd into whatever directory name that you have. So this is to change directory. It's as if I was in one folder and I was going to this folder or entering this folder. So that's change directory. ls, whatever directory you're listing, the directory contents, all the files that might be inside. I'm going to skip to pwd, that displays the full pathway of what current directory you're in. So for example, if you're in this folder, it would list out this sort of directory pathway. And then because we have Python installed, the nice thing is that we can execute a Python file with this command Python, and then you enter in the file name. And if you're not familiar with certain symbols or characters, this period is the current directory. So it's the current folder that the terminal is in. And then 2 periods is the parent directory. So you can navigate up and down. And one handy tip that I like is that you can just use tab to autocomplete certain pathways. If you have part of the folder name, you can complete it. So if you want to get started, let's just check that Python is installed first. So you can just run this very simple command, Python v for your version. Have it installed. And you should see something like this where we have the version. And if you guys are having trouble, feel free to stop or ask questions. That is no problem. And so just the easy thing to do is unzip the codex folder because we want to access this source code that is included with the tool. And so if you were to download this tool or clone it from GitHub, you would go through a similar process. And so you now have access in codex main. to all the files that we use. So you should see something like this after you're done extracting. And then after that, it would be a good idea to have your terminal open. So this is mine, but just have that. And then if you can change the directory to where you have installed the codecs to. Right, so I have it unzipped. And if I were to list the contents, I see that codecs is right. I guess it's pretty small. See that codecs is right here. So I'm just going to do CD codecs. But this differs for wherever you have it installed, so just do so accordingly. I'll give you a second for that. Yeah, and just to mention, because we want this to be a Python package, if you CD into this second codex, that might be too far. So just stay on the root level where you see all of these files. And your terminal should reflect that you're at the first codex level. Part of making codecs adaptable to Python is that we've used several Python packages, very common ones such as NumPy, Matplotlib, and Pandas to just help with the analysis. So remember in that first codecs directory, you can run this little command right here, pip install and then period. What it does is that there's a list of packages and they'll auto install as you install codecs itself. I'm in the wrong one. See all these files. So you should see something like this where it says successfully installed codecs. And that means that all the necessary dependencies were installed. And one thing nice about this method of installation is that it can also be used as a Python module. So there is supported functionality for that if you were to use this in your own code as well. So if we're all good on the installation, we're just going to do a quick crash course of what kinds of materials codecs requires for its experiment. So we mentioned things such as data sets and various binning schemes. So we're going to go through those really quick. And different codecs uses different files to locate these materials that are needed for your experiment. So first one, of course, is your data set. We mentioned that it's going to be a tabular data set because of the combinatorial nature of things like CC and SDCC. Information should be organized into columns and rows. So right now, we use CSV files as the data set format. And so columns will be the features that you're computing over, and then the rows will be the various samples. So just have an example here of iris. If you're familiar with that data set, you have your features up top and you have each sample going down. One important note is that a sample ID column you should include just because various modes require unique identifiers for these samples. The next sort of input file is known as the binning file, and this is because we need a method to construct that universe that we were talking about, this universe of defined features and values. And so because there are defined features and values, this means that continuous features do require discretization, and this is done via the binning file. And what you'll find in a typical binning file is this sort of format where it has the feature and then its possible values that appear in the data set. And if you notice is that these bins are custom made. And so what we were saying about the need for a method to create binning schemes is that currently it does require some knowledge on your part of how you want to bin your data. But in some sense, this is nice because you can bin the data to what makes semantic sense. So for example, if you had season as a feature, you wouldn't want to do it out of order, such as summer, winter, autumn, spring. You'd want to go in order. So like spring, summer, autumn, winter. So that is the advantage of the binning file. You can specify the order or the size of the bins if you don't want them to be even. And this is used to construct the whole universe for the codex experiment. So yeah, it does require some knowledge on your part. But if you're familiar with your data set, that should be no issue. The next sort of input requirement is the config file. And this is the main entry point at which Codex is interacting with to locate all these materials. So things such as the data set file, such as the binning file, these are specified in the config file. And so what we have here is a list of essential inputs, I guess we can call them. And these are required for every Codex mode. So just to highlight a few of these, we have mode, which is the actual experimental function that we want to run. We have a predefined list of them, and they all do different levels of analyses. So you can take and pick. There is a description of modes on our GitHub if you're curious. The next two are the codex directory and the output directory. We'll touch on the codex directory in a second, but the output directory is for this experiment that this config file is designating. We can have a landing spot for our results. Data set name and model name are just for your convenience so that you can label what is the name of your data set. You can specify the version as well. And then config ID is the unique ID to hopefully identify your experiment. So when you run it, it will be saved with that name. And like I said, the paths to the data set file, the binning file are provided here. So Codex knows where to look for them. Sample ID column, this is to designate in your data set what column is the sample column so it knows not to compute coverage over. T is a list of integers specifying the strengths of those combinations. So we have one-way combinations, which are just feature and level. But as you can see here, we have 2 and 3. So these are two-way combinations like those pairwise features, but also you can even go higher. And just as a caveat to that, the strength of your combination cannot exceed the number of features that you're computing coverage over. That makes sense. You can't combine more features than you're computing over. So, and yeah, the list of features as they appear in your data set. So Codex knows what features in your data set to compute coverage over. So hopefully you're able to gather of just what is required of a most minimal of Codex experiments. So to kind of organize all of those files in your head, I wanted to touch on something that we call a Codex directory. And so because it's reading in so many files at once, it might be a good idea to consolidate and organize all these input materials for your experiment in what we call a Codex directory. So if you think of the various data sets that you use on a daily basis, these are simple ones like the Titanic data set or the Palmer Penguins data set or the Iris data set. These will have their own specific data set files, their own specific binning files, and even things like machine learning model performance data associated with them. And so for the ease of codex use, it's a good idea to have a directory containing those sorts of materials in one place. And this is good for reusability, allowing reuse of a data set, or in the case that you want to use a slightly different version of the data set, it's all organized in one place. So there's a command that codex includes to construct a generic sort of directory. And so you don't have to do this with me, but I just wanted to show you of what that might look like. So this command right here, it's saying it wants to make a new codex directory, and then you can name it whatever you want, and it will auto-construct this kind of codex directory. So we go. And I'll just call this, yeah, we'll call it Iris.
In complex data sets, performance, rungs.
Just, if you need a bit of starter help, there is functionality for that. So as you can see, it created these different sort of pre-made structures to what you might need in your experiments. All right. And so as you go through these experiments with your data set, you might see it populate with various configs that you have, or like I said, if you have slightly altered versions of your data set, you can all keep them in one place without having to pull from every part of your file system. All right, so now we're gonna get to hopefully the fun part where we get to run a codex experiment and see it in action. So the first, I guess, most basic mode that we can touch on is data set evaluation. And this gets at the question, we were talking about identifying gaps in your data set, and also just surveying the data set for how well it covers that defined universe that we were saying we would construct. So if you have a defined universe of what you think your input space would be, you want to see, does this data set and how well does it cover the possible features and values that it includes. And so for this, we'll obviously need the data set, and then also the binning as our way of constructing the universe, and then our specified strengths of T for what interactions we want to witness. And so the command to this, for those following along, if you'd like to enter this with me, we're going to run this Python command. We're going to give it codex/codex, which is the main script. What's that?
Which location are you now in your?
Yeah, good question. I'm in codex main. So this is the top of the repository. And by running codex/codex.python, we are accessing the actual script that runs it.
So when I did the iris, it created a directory above. So it created iris under the codex.
Yeah, so the question was when you created the directory iris, it would create it in the parent one. That's just the default. You can specify wherever you want to put that parent directory. Luckily, we won't need it for this one because we're going to be running on a pretty cool data set that we've been working closely with. So I'm actually just going to fill in codex/codex Python and leave this for now because we want to see this apply to a real data set, right? So This is rare planes. It's a image computer vision data set. It is 253 satellite images, overhead imagery of planes that are landed. And this is distributed among over 8,000 tile images. And so you might wonder, what are the features that we are computing over? You can compute coverage over metadata as well, right? If we're talking about the context that you might see a sample encounter, this is a perfectly viable option, sort of as a surrogate for computing coverage over. Each of these images where there are multiple planes, they correspond to one of these rows. And so we've done additional pre-processing, but the idea is that every image has associated metadata where there are those features and values. So the ones that we are running with are like hour of day, or the average pan resolution of which this image was taken at, the off nadir max, forgot what that one is, but also the biome that these planes are in, and also the season in which this was taken. So these are like real features that you might want to see how they interact. For example, like, will my data set have, will it be missing any interactions of like jungle in the winter? Most likely, because it doesn't, that winter context is not looks similar in the jungle all throughout the whole year. That's just one example. All right, so now that we have some knowledge of our data set, I've given you a pre-filled out config file. And so what we mentioned about the codex directory, that's going to be our codex directory for today. It's going to be under tutorial/configs/ this JSON file right here. So you can see that we've specified where we want the experiments to go, what we want to call it, and also the features that we're using, the strengths. And so if you'd like to follow along, we have the command to run the script, but also we need to give it that input. So it's going to be in tutorial, again, configs, and then just look for this one, config rare planes example. So as you can see, it's done running, and you will have the results that came out of that. And if you're wondering, what was that good for, maybe we can glean something out of this data set.
Right, can you pause?
Yeah.
Just check.
Oh yeah, yeah. We can take some time for that. This is not easy at first.
So it's the depths. Iris.
So not the iris folder, but
Tutorial runs.
yeah. So this path right here, this was created from how I had it in that pre-filled config. So you never got to do it. So that's too bad, but you can still find it. It actually might be helpful.
Let's go to tutorial run.
Well, first, let's look at where we said it should go, right? So the output directory was tutorial/runs. So we can look for it there. Got tutorial. Wait.
And the config file is in that configs.
What's that?
The config file where is that the tutorial configs folder, the one that you just showed?
Yeah, that's under tutorial/configs.
Yeah.
So these images, they just got run, right?
Yeah.
Because-
Do you see them on your? Yeah.
Yeah, how do I read the, wasn't clear how we can read
The one-way binary coverage for road plans and all those, they just got generated, right?
Was in your runs folder. Great.
It takes some time explaining some of those.
Yeah, we will. Yeah. We're just trying to have them run it too.
So when you're reading this.
Yeah.
So I'm seeing on the x-axis, number of interactions. So I'm trying to understand.
Yeah, that's
So
what
you
I,
have combinations and then you have, so how does what's the difference between the x-axis?
yeah, that's what I'm telling him.
Oh.
Go over that, no,
Yeah, it's not too interpretable, but I'll help you through it.
But you take one or two of those things and just go with it. You know, the x-axis, y-axis, what this diagram actually shows.
Yeah.
What is the?
It's like portion of appearances per every.
The one that I showed, it's called CFD, combination. So that's another tool. That one is the CFD.
So it is the first year.
Oh, this, oh, yeah, no, this one is, this is not the frequency. That's why I think Ryan is going to go with that. This is not the season, these are the.
Oh,
That's combination.
That's coming. Well, that's some that's gonna be good.
It's in the result of that product.
How are we doing, Erin?
So it's just telling you.
Yeah. So as you get to where these results are stored, hopefully I had a little trouble finding mine, but now that we have this, right, as we said, where is it? Because we ID'd it under example DE rare planes, we can navigate to this folder right here and we see that we have the results. So there's the info log of what transpired during the experiment. And so we have some results, and so we can go through some of them. So when you're thinking of coverage, you know, we mentioned the binary case where do you even have this feature or not? Right. So maybe let's examine the T=1 combination case. Right. And so this might be a little difficult to look at. But what this is getting at is that for these, there are these features. And then this is the maximum number of combination across these interactions. Sorry, yes. So that is the values or the interactions of multiple features. And so biome has 12 levels to them. And so that's why this axis is up to 12. And so what we see is that this gray area on biome means that this interaction is not present. And so we'll get to how to find out what that interaction actually is, but we can see that there are, I guess you can call it gaps in our data, that this interaction is not covered. But for the other ones, it looks like the data set does contain them. So all hours of day are present, all levels of off-nadir max, but perhaps things get a little.
Brian, could you quickly just show the input data that was used to generate this?
Oh yeah, that's a good point.
Yeah, just show that for people have a sense of the.
That's right. Yeah, so if you're wondering what even
What got into the input produce. Yeah.
right. So your data set might look like something like this. Again, we have those features of your data. And so the idea is we are looking at for different, given the list of features that we gave, we are looking at what interactions are present among all of these samples.
And you also did some bidding in between, right?
Yes.
So, this is the raw data. Then there was some bid data, so you can maybe show the data as well.
Yeah, Raunak is giving good points because there are, because we gave it a binning scheme, there's also a bin version of the data set. So as you can see, because we had to bin a variable like hour of day, we have this bin associated with it. So this value, maybe let's go to the top. So this value of 12.183, that is encapsulated in, where is it? This one. This bin right here. Right, so then we have a discrete number of levels that we have for this hour of day feature. And that's why we are able to assemble something like this, where there are a defined number of values for this feature. Yeah, so maybe we can go one step further and look at what does this look like for t=2 combinations, where there are two features interacting. And so things get a little bit dicier here, but we can see that, for example, when you cross these features, you might have more interactions missing. So again, this is the maximum number of interactions across these combinations of features, and we see that we have a lot more missing, as indicated by the gray.
Yeah, just pick any one, like the out of day and season, and there are some value combinations that are not there in the data set. So.
Right. So, because we saw that one level of biome was missing, we can see that it sort of reverberates at t=2 and most likely t=3 levels, because these features involving biome are missing more. So hour, day, and biome, we see that it will not be present because that level of biome was not present. And there are different versions of these plots. For example, there's this one of the raw counts. So we had the binary coverage, does it have it or not, but also how many of it are present. So that level of biome, of course, is 0, so there's nothing. But this level of off-nadir max, maybe we see that there's a disproportionate amount of this third level right here. And then same applies to the t=2 level. We see that some interactions are more frequently appearing and some are less. Another style of plot is this proportion frequency. So of this combination, this color is indicating what proportion of these appearing interactions how much it appears. So this will be on a scale of 0 to 1. And that more frequent off-nadir max, you can see is taking up more of the samples that take one of these values. And again, looking at the t=2 case, they kind of even out because there are so many more interactions, but we can see that we can at least see that there are some more present than others or more frequent. And then the last thing I wanted to show you from this was this coverage JSON. And this is just a holistic report of what was your data set. So not only what universe did we use of these features and values, but also we have the actual CC metric. So for the t=1 level, we see that 96% of interactions are covered. And why it's not 100%, we have that one level of biome to blame. So luckily, this coverage report also includes missing interactions. So at the t=1 level, we can see that tropical and subtropical coniferous forests never appeared on our data set. And so that's something to keep in mind with whatever we're doing, whether we design test cases or we compare training and tests, we know that this interaction never appears. And so extending that to t=2, the coverage drops. Now only out of all two-way interactions, we can see from this report that only around 68% of these interactions are covered. And then in finding what's missing, after going through all these counts, you can see not only what features and values are missing, but the combinations of features and values are missing. So in this case, you would look at it like this window of hour of day and this window of the off-nadir max will never appear in this data set. And so we can say these are missing interactions from our data set. Any questions so far?
Does it count interactions in the report? Setting feel like it's 30.
It doesn't cap the number of interactions. Are you saying that it appears in the plot? No, this is however many interactions appear. So it might take some scrolling, but at least it gives you the whole list of what's in your data set.
Well, I'm going to interject that, and this is academic code. This is the tool that we developed in order to come up with new methods and metrics. And so the coverage.json, as we are using it right now, is not really intended to be like, here's a readable report. It's mostly intended to capture the outputs. And we're using things from the JSON as inputs to other things, like the universe who can grab it in the JSON format and reuse it. So if it's user unfriendly, we agree and we apologize. That is something we're working on.
Yeah, so if you are online and didn't hear, the kind of more academic nature of this code makes some things like this hard to read. And so maybe it's not really meant for that, but you can grab what information out of this coverage JSON for your analysis.
Can you show the missing.txt?
Oh yeah.
Easier to digest for that particular
Sure.
and the other one too, the not missing, which will be able to report.
Yeah, so I mean, luckily, if you wanted something a little more readable, there are these sorts of files. Right, so starting with missing interactions, it literally explicitly lists out every interaction that's missing. So this is t=3. We see that we have a lot of three-way interactions that are not included in this data set.
Then you can also easily see the CC values and
yeah. on the left side. So if you're curious about how we got this proportion, it is the number of interactions appearing versus the total possible number of appearing interactions given how we define our universe. So that's how we have this 0.33 for our combinatorial coverage. All right, so if we have no issues with that, yeah, we already went through all these. Just how to read these plots. There's also another mode that we can touch on. Data set split evaluation. So what this one gets at is between two portions of a data set, what exactly is that relationship? Like what Erin was talking about with these cases, what of those T-way interactions are present in one subset but not the other? And so specifically for codecs, we have it so that you can examine portions that are a training set and a test set, and even a validation set, and see the relationship between those three. So the additional, I guess, input requirement is that you would need a way to assign what samples belong to which portion, like which samples are in train, which samples in tests. You don't want to mix those. So it requires something called a split file. And this is just one case of codecs, depending on the mode, requiring just some more input materials. So as you can see, this is our config file. Looks a little different because we have this area for designating the split file. And I can pull up what that looks like, but codecs will know because it reads the config file and it will look for this split file, which we can pull up. So it said we were storing them, right? The split folder is under splits. And then we can look at this rare plane split. And so we can see that under train, we have a list of samples that we want to designate as the training set, samples for our validation set, and those for our test set. And so these sample IDs, why I mentioned the sample column when explaining the data set, let me pull that up too, is because it needs a way to know which partition or which portion of the data set it belongs to. So these IDs are as they appear in the data set. So if you're able to provide those, you can have a split file and then you're able to run dataset split evaluation. So once again, it references based on these paths you give it. And one more time, if you're following along, we're gonna run this same program, but this time you see this different file name. It's config rare planes example DSE for dataset split evaluation. So if you'd like to follow along, please do. It's the same process. Again, it is a different split file. So if we run this, I'm getting permission denied. That's weird.
Is it because you have it open?
Oh, you know
Like
what? Yeah,
locked?
it's because I have this open. One second. Okay, no cells open. Let's try one more time. Again, it's finding Same binding file, same data set, but this time we are providing what is the training and test split. So it's saying that results were saved to that same directory under this folder. So let's check it out. I can see it's right here. So in this, as a result of dataset split evaluation, we have the same CC sort of plots, but this time we can see them by each portion of the dataset. So we wanted to know what is present, what is absent in our training set. We have this on just the training set. This is a two-way binary coverage, so does it have it, does it not? But we also have the same for test. And so just at a glance, you can see that there are a lot more two-way interactions missing in the test set than there are the training set. And that is reflected in the combinatorial coverage metric at the top. I'm curious for T equals 3 as well. Yeah, even less.
This one is the CC is showing the percentage of coverage, right? The 26%.
Of the universe, yeah.
Yeah.
And so since the test set is so much smaller than the training set, it's natural. We would expect there to be more missing because there's fewer opportunities to cover things. I think there's a question at the back.
I'm wondering like how I can interpret this to generate insights.
Okay, so the question was, how can I interpret this to generate insights about my data set? So some interpretations, if an interaction is missing from the training data set, one application, that model never saw that. So as a tester, that may be a great place for me to generate.
Would you like to?
Yeah.
Yeah. It's a great question is how can we
Repeat the question.
Yeah, so the question from the room was, how can I use these plots to generate insights about my data set? And so some simple ways, simple takeaways are that the binary coverage of the training data set, any gaps in the binary coverage tell you that that model never saw those interactions in training. And so we could, as testers, hypothesize that the model may not have good performance over those interactions. We can't say that it will have poor performance in the gaps, but it might not do well. It's not things that it saw in training. So as testers, we might want to think about generating test sets that cover those gaps. We might think about putting samples specifically in those locations. I think that's probably, did that answer your question? Is that useful? Okay. Cool.
So all those same plots are exist, but now it's nice because you can divvy them up by training or test. It's not reflected in the title, but in the file name, you know which one is train and which one is test. But one new plot that is part of dataset split evaluation, and this is just because of each mode has a slightly different flavor of an analysis. This is a I guess, what do we call this plot? SDCC plot.
Set difference.
Yeah. So this is looking at set difference. And so if you don't want to look at the CC plots are less interpretable for finding this information. But in terms of seeing what is in one set that doesn't appear in another, there are these sorts of plots. Again, same universe that we define across train and test, but we can see, let's start with one way. We can see that, in that direction of what is in train not appearing in test, or what is in test not appearing in train, this plot is supposed to get at. So these in the red are saying that these are in both test and train, that they're in the intersection. Or you have certain interactions that are in the set difference, so that are in test not appearing in train. There are also those in neither set, which is the ones that were completely absent from our data, like we mentioned about those tropical and coniferous forests for biome. Or we have those that are not in this training set. And so you can kind of draw where each training or test set covers, and therefore, use that information for analyses.
So to answer the earlier question again, with respect to set difference combinatorial coverage, we can think about what some of our research results have shown is that when the test set is very far away from the training set in terms of the interactions that are contained, the model tends to have worse performance on that test set. In other words, it's a more challenging, it's a more different test set. And so we could expect then that the set difference combinatorial coverage, remember, it's a difference metric. So when it's 0, that means they're the same. And when it's 1, it means they're very far apart. So as the difference becomes small, these, for example, when we're computing it in the direction of test not in train, that is a more challenging test set. And when when the SDCC is small, there are many things in the intersection and there are very few things in the set difference, then we would expect that to be a more representative test set. Helpful?
Does the software compute the, I guess, the frequency of the, like the significance of the intersections and differences? Like, so for instance, you could weight it by number of occurrences and that.
So this one is focusing on the difference only, not how frequently something is appearing.
Well, I mean, like, for instance, you could weight, how many how many interactions are not in the set or in the set difference, for instance.
The summary.
Okay, so the SDCC does.
Yeah, I mean, we can probably get that. I don't know whether it produces that. That is just some summary data statistic about the number of different combinations that are present in training, but not in test, and vice versa.
So the SDCC is going to be a proportion metric. So it's going to be a percentage of the, so if I'm computing the set difference of T minus S, let's say, target minus source, whatever that means for us in this scenario, the SDCC value is the proportion of interactions that appear in the target that don't appear in the source. So if I have, let's say I have 100 interactions in the target and I have 50 interactions in this, I have 50 interactions that appear in the target that do not appear in the source. They're missing from the source domain. Then I would say I have 50% or 0.5 SDCC.
Okay, but like, for instance, if I had 50 data points of a particular kind of interaction, like a single interaction, or one, this metric would not detect that subtlety.
Yeah, this, as we are discussing it right now, SDCC is a binary metric. It is not a frequency metric. Our work on, at least our work on the VT side, our work on frequency coverage is pretty nascent. We've been doing it over the last year. The NIST team has had a lot more work in looking at frequencies, combination frequencies, and combination frequency differencing. But what we apply, like what we're thinking about measuring, is a little different between the two teams.
Okay, thanks.
Mm-hmm.
Cool. So just as a bonus objective, maybe we can write and run a custom experiment if you are still following along. There's a lot, so you can watch me do it as well. So if you want to do this on your own, so in this tutorial codex directory, we have something we call the abstract data set. This is just to simplify things for us. We're just thinking of A, B, C, and D in our data set. Once again, we have an ID column, and we have different values, both continuous and discrete. Right. So this is what our data set looks like. Go ahead and close this. And so for now, I'm just going to select what features I would like to compute coverage over. And just make a mental note of those. I'm gonna do all of them just because just to be a completionist. And so this is information that you'd probably be able to find about your data set. So what are the appearing values for your discrete, your categorical variables? We have these for A, C, and D. But for B, we can sort of plan a binning scheme around these continuous ones as well. And so just some nitpicky formatting that we have to do. We'll separate values by semicolons. We'll separate the feature, when we bin, sorry, we'll separate the feature names with this colon. And when binning continuous variables, we'll use interval notations to include the maximum and minimum values, so nobody is left out. Right, so yes, we chose our features, but you would write a binning file, and I just put in question marks here, but using what we know about the data set, we're just going to write out those levels. And we saw that it goes from 0 to 30. So let's do a high to low sort of scheme. Just 2 bins for this one.
Question.
Yeah, question.
Code cover those features for you, like calculate the deviation of variables, or you have to do that before.
Yeah, so the question was, can Codex run the statistics on your data set to produce binning schemes? Yeah, we do not include statistical analysis of your data set in Codex. We assume that that is well handled by other packages. Weka is probably a good tool for producing that. We do, however, have the ability to learn from your data to create the universe by just parsing through the data, but that does not. So if you have just categorical variables, if it finds something it doesn't know about, it'll add it to the list and it'll pull the features, but yeah, but it will not handle, if it sees continuous features, every new continuous feature, it's going to assume it's categorical, it's going to add it. Yeah.
That's why Erin was saying it's an unsolved problem of how do you bin something. You know, you could put into quartiles, but is that interesting? Is that accurate? It's a different question.
Sensitive decision you make when you define your bidding.
It is likely really sensitive. So the question was, how sensitive is coverage to your input parameter model? And odds are it's pretty sensitive. So for example, if Brian makes right now he has B split in 2 halves. And if he made B split from 0 to 29.95, et cetera, you would get very different coverage analysis, assuming that those values were fairly well spread.
Yeah, so that's why user knowledge is good, because if you make a bin that's tiny, it will treat that as like an unseen interaction, and so that's just something to keep in mind. So yeah, we've written our binning file. Not too hard for this A, B, C, and D, so that's nice. But I guess this config file might give us some trouble, but we'll work through it. So for this mode, you can find oh yeah, this is pretty small. So in terms of what modes are offered, you can find documentation on our GitHub for codecs. So we're just going to do data set evaluation again, nice and simple. Let's keep these directories. I'm going to call this hands-on for this abstract data set. I'm going to come down here. Now, what is our data set file? These are the things that you might have to know and prepare. So it says dataset abstract.csv. What sorts of features do we want? I said all of them, so let's go A, B. What was the binning file? We see that we call it binning abstract.txt. Our sample ID column, just called ID. And dataset evaluation does not use this, so we will ignore this. And then what T's do we want? Should we go all 3? Maybe 4, just for the fun. All right, so looks like we have everything filled out for our config file. And so the last thing to do is simply run it. And we're going to use the same command that we've always been using. But this time, what was this config file called? Config abstract example. And so the experiment is done. And we can see that our abstract example worked. So this is the frequency coverage, just the raw counts. We can see that every feature is covered from A, B, C, and D. Yeah, that's good. And fairly even distribution as well. So these are the sorts of things that these codecs results will tell you.
You look at the 4-way.
Oh yeah, we never looked at a 4-way, so yeah. Because there's only one 4-way combination, these are all the possible interactions for that one combination. Yeah, do with this what you will.
And then do you have prepared to do a different binning scheme?
Well, we could do that on the fly. We can do a different binning scheme as well. Maybe like we were talking about, we can do like a tiny bin right there. Just to be silly. Maybe we could do a medium-sized one. Interval notation. And we'll just keep the last one. So now there are 4 bins, all different sizes, because I wasn't paying attention. Does that look right? Okay. And because we're referencing the same binning file right here, if we rerun, it should rerun with that binning scheme this time.
And obviously, if you wanted to save the previous results and then run this with a new binning scheme, you could give it a new experiment name, and then you would be able to compare outputs.
Yeah. And so because we made that first bin of B tiny, we can see that not too many samples are appearing in that one. So how you bin can greatly affect what results you get. Whereas this one, which was 15 to 30, half of the entire range, it's gathering most of those samples.
Okay.
Yeah.
Anything else that we want to go over?
I think that's it.
Okay.
Yeah.
Awesome. Thank you, Brian. I know there were a couple, we had some, dead computers or software that didn't install properly. So I want to invite you to reach out to us. We are happy to hop on a Zoom call or Teams call and, walk through the software, get your feedback, especially if you find bugs. Please let us know because we would love to improve Codex. So far, the testers have pretty much been Brian, myself, and then Dr. Kamitas helped us out. But we would love to get more feedback from a larger set of individuals using it. So now we have about 24 minutes remaining with you all. And what we would like to do for the last portion is have a discussion about practical challenges of using combinatorial testing or challenges that you have that you think combinatorial testing could be applied to. So I would like to ask the speakers to join me here so that we can have a discussion and get the different insights from the speakers. So Raunak, if you and Rick would join. And we're still sharing the screen.
Okay.
Yeah, that is okay. I can't, Jagan, I'm just gonna ask you to unmute yourself and interject yourself if you have something to say. I can't see the Zoom right now with the way everything is set up. Maybe I can I'm not sure. I'm scared of the computer. So, and similarly, if there's someone online who has a question, if you could monitor the online and interject that.
Sure.
Thank you. So we did have some feedback, some questions on the form that we sent out. And so we're going to start with those. So the first kind of question that came through the form was a need to identify input features that should be explored for impacts on AI performance in developmental testing. So potential exploration of anomalies in combinatorial testing or to identify subgroups of data to have human analysts explore. So my take, and again, Brian, please clarify if we don't understand your point correctly. I think that some of the work that we've done on, for example, the systematic inclusion-exclusion experimentation of trying to figure out which are the critical factors that impact a model could be a starting point for this. Another starting point for this is when we run combinatorial testing and we find that, for example, some interactions have lower performance than others. We may be able to then follow that up with adaptive testing or other fault location techniques that combinatorial testing uses to try to dial into what's going on within those interactions. But I do also want to say that generally combinatorial testing there is some use of, for example, locating arrays to do screening experiments. But generally, it's detecting issues, and you cannot necessarily use combinatorial testing to attribute variance. So you can't do like an ANOVA with combinatorial testing. And so you may then want to take those interactions that had different performance and apply some kind of design of experiments approach to try to attribute the variance, why things are failing, and to what root cause. And then I would love to get your insights.
So another, in addition to what Erin's pointed out, another way that we've looked at this particular question of, how do we identify input features that have a stronger influence on the question, the output that we're looking at? The one example that we only had up briefly was the physical unclonable functions one, where the idea there was to identify certain combinations that had a greater influence on the output. The physical unclonable functions, the output should look almost totally random. And so if you remember the graph that we had there, we had a very busy graph that had a lot of difference across the center line, and then a much quieter graph that had just a few little points extending away from the center line. That's one case, one example of where we can apply that frequency differencing approach to look at whether certain combinations have more influence. In that case, lots of the combinations had more influence, and they won the PUF, the physical unclonable function that was harder to defeat, had just a little variation from the center line, but even there we could see a few points that would stick up, and those we report the combinations that are associated with those. So we could, in that case, visually see that there was a huge difference, and we could then narrow in on the particular combinations that seem to have an impact.
So in the case of the physically unclonable functions, the idea was that these are actually hardware that are used to sort of authenticate that this is going to produce some specific functions that you cannot clone. And then people actually try to attack it using some sort of machine learning algorithm. So what we did is that we tried to look at a particular physical unclonable function, a PUF, just look at the input, output, and the combinations and how frequently they are present in the output that it is producing. And looking at that, we were trying to predict, is this going to be easily attacked? Is an ML will be able to actually replicate it easily or not? And that was an initial frequency differencing analysis that allowed us to actually give an idea that, yeah, this PUF is strong, this is pretty weak.
Yeah, I'll kind of elaborate on the question. Like, I think after hearing the presentations and things like that, this is a little more out of scope of kind of what you guys have been talking about. As it's also kind of thinking if there are confounding factors that aren't necessarily labeled in a data set, thinking medical applications, you might have rulers for kind of morbid samples or people lying down that it picks up on. So is there a way to look into that? I think that's kind of a separate idea from this, where it's really, this is kind of planning how to collect your data or to figure out what don't we know about a lot of these things, rather than looking at that kind of performance more explicitly, especially when you get stochastic kind of system.
Yep. I'm gonna go to the next one. So the next need was defining levels of detail desired in dataset labels and features. For example, you're faced with a data set that does not contain many operationally relevant features or with lower granularity than desired. And so my take on this is that one of the uses of combinatorial testing that might be applicable here is to determine that your data set doesn't contain many operationally relevant features because of that set difference combinatorial coverage or a kind of future combinatorial frequency differencing types of approaches. In both cases, we still need a defined universe. We still need some way of generating that input parameter model. But we could think about using, combinatorial coverage from that defined universe against the data set, whether that's the training data set or the test data set, to figure out where those gaps are. Do you want to refine this question before, or is this?
No, I think that makes sense too. And I think one of the ongoing needs will be kind of like the subject matter experts will be a good one, but do these models understand the world in similar ways that the subject matter experts do is kind of a whole separate thing too.
Yeah, and so again, getting back to the frequency differencing question, this is the kind of thing where you see a distinction between, if we're looking at a machine learning example trying to classify something that is like the output of a physical process, then you tend to have a lot stronger results, better results, higher accuracy than if we're looking at, say, healthcare data, where you're trying to identify the presence of disease or a trend because there's so much random variation. And in those cases, again, you'll see,
a graph that has fewer differences, or the differences are sort of fuzzy and spread out, as opposed to the physical system where you can have much stronger differences, stronger peaks. That's something that we really need to look at a lot more, because it's not as simple as it sounds. It sounds like it ought to be easy to spot the differences, but there's so much variation, and it's a research question. That's the best I could say there.
Do you want to add anything or?
No, this is definitely one of the areas we need to explore, and the desired, I mean, even when you have very well-defined, well-binned scenarios, you still need to ask the question, is this the right level of granularity for the type of analysis we are doing or not? So, but it's the way we look at it, it's a different research question, but it's another important research, a set of research questions, I would say.
So somewhat tangential, but any thoughts on, because like some of the combinations aren't showing up because there are underlying constraints, in your data about what is a valid entry in your database. Have you thought a bit about like how to separate those two cases out, where it's, you're actually missing something versus you're not missing something and there's underlying constraints?
Yeah, I mean, that's a really important question, because you've almost always got that happening, right? And so one way that we've tried looking at it is, if you have a really large sample, assuming that is the universe of possible values, because we don't know what the constraints are typically. So in that case, you have to make certain, different assumptions, assuming that your training data and test data, that's all there is. And that's, again, that's one of the big differences between the machine learning problem and the software testing problem. We're not going to know necessarily what the universe of possible values is. So there again, we've got to make assumptions, and we don't know where that research is leading. You could see a trend here. There's a whole lot of research questions. So if you're interested in publishing and doing this research, it's great opportunities.
Yeah, we have problems for sure.
There are no problems, only opportunities.
And just to pique your interest a little more, it is entirely possible that you take this approach and you ask the question as to, can I discover some of the constraints that I don't know about from just analyzing what is continuously absent in the data set, right? So it is also possible to do exploration in that area as to discovering the constraints that we thought doesn't exist, but it's not showing up in the sample.
It's essentially along the lines of what I was thinking about, is, I see a bunch of big data sets and don't really have much documentation. So I think it's a very practical problem to try to figure out. Right?
Yeah, and one thing that these tools and the approach has shown is that it gives you an approach or a methodology towards exploring the data and getting a sense about the characteristics of the data from the perspective of interactions present in there. And that can lead towards a lot of other information that you can potentially infer. And we have probably just only started to scratch the surface in that area.
The third need was templates of metadata deliverables we could request from programs and recommended tools for developers or others to create these deliverables. We have almost no ideas on this, at least when we were chatting. I think that something that our work has started to provide is this methodology for identifying the metadata that is impactful for the model. I've done some of this work for real programs where the amount of metadata, like the number of columns in a metadata file, was massive. And so if you were if you don't know which metadata are impactful and you're just saying, well, just give me everything you have. Some of this metadata was like file location, and that's not going to matter. So, possibly some of these approaches could be that first step to saying, given the metadata that was here is what we have found to likely be important. And then also, as we apply these approaches to different domains, it is very likely that metadata that's impactful for computer vision of detecting planes may also be impactful for, autonomous vehicles, trucks, or other problems that have a similar flavor. So maybe we could start to collect those lessons learned and best practices across different programs and say, this is what we found before, so maybe carry that forward. Do you have any?
Yeah, just to reinforce what Erin said about different programs, different domains, the metadata weather prediction is going to be a lot different than animal identification, that kind of thing. But there again, there's an awful lot of good research out there that people use, just the basic scientific research going back 100 years. If we wanted to figure out what's the important metadata for weather prediction, then the meteorologists have ways of categorizing these things. Need to look into those a lot more. Again, yeah, this is very much the research question.
I'm understanding the problem correctly, but could you just, upon importing everything, you may not want everything, but could you do like a traditional Sobel sensitivity analysis or something and just see like if there's a variable here that's just not predictive of anything, if it is noise, it's not going to help throw it out before you begin your analysis. Is that the kind of thing you're talking about?
So I may not be understanding your clarification too.
So we did do a little bit of comparison about our frequency differencing in what we didn't cover one of the recent studies, where what we did is we looked at the model, the training data set that was being used to train, and we asked the question, do I really need this? Can I shrink it and still train the model in a relatively similar level of accuracy or strength? And to reduce that, what we did is we tried to look at, okay, what is the frequency of combinations present? And the frequency of combinations that are present, the ones that were higher, let's say we said that, okay, these are the good samples. And then take those and try to use that to train the model. And then we try to compare it with some of those Sobel sensitivity analysis and others that just to do it. It was a very preliminary study. It was just like the first step towards that. And our approach of simply using the CFD, the combinatorial frequency differencing, how frequently the subtrain combinations, were a pretty good method of trying to identify which samples are useful for having in your training set. But as I said, this was like sort of like the very first step of trying to do that comparison in terms of trying to figure out which ones are good.
And keep in mind, just keep in mind that there may be individual factors that looked at individually, they don't seem very interesting or useful, but suddenly you might determine that when these two factors are looked at as pairs or within triples, then they suddenly become more important because there's some particular combination there that makes the difference. That's the other thing that we really want to do is we've got lots of good data on the interaction strength of factors and combinations that cause failures in conventional software. What's the distribution of factor combinations that matter in machine learning? And this gets back to the previous discussion. It probably varies a lot within different application domains, but that's something that we need a lot more data on as well.
And I just wanted to clarify further that when we're thinking about metadata, we're thinking about data that's not directly used by the model. And so if you're thinking about what is predictive, metadata won't be predictive of a class. But it could still, like, we can think about if camera angle and time of day, which creates shadows. If that modifies the way an object appears, its time of day or angle is not going to be predictive of the fact that it's a truck, but those conditions could impact, if not seen in training, your model doesn't know that a truck looks like that has a long shadow at time of day, and it kind of warps the way it appears. And so that's why at least the work that we did on systematic inclusion exclusion, we really think that you cannot figure out which factors are going to impact your model by just looking at either the data without a model or looking at a trained model where we haven't manipulated the training data in the way that we did. Because if I just say, okay, I have a trained model, which interactions does it have better or worse performance? That doesn't tell you that it would have had better or worse performance had it not seen those examples. So we really do think that you have to have this kind of designed approach of withholding some information and seeing if it has an impact. Recommended strategies for testing based on results of combinatorial coverage. How to apply design of experiments when we have one or more areas with sparse data, especially with hard to change factors like environments. I think my interpretation of this is how do we use combinatorial testing along with other approaches? There is some work on, at least for software, I can't remember. There was some work of using locating arrays for screening experiments and then following that up with DOE to do kind of ANOVA. But I think that this is really an open question is what are the strengths of different approaches? When should you use which ones? And can we also use them in conjunction? Is there anything to add?
Well, this just to simplify a little bit, but not too much. This question is like that graph. If you think back to the coverage put up where we had the upper right corner was the reddish orange. Those are the combinations we haven't looked at. We don't know anything about. So this is, in terms of recommended strategies for testing based on combinatorial coverage, that's sort of the first thing you want to look at. These are combinations that haven't been tested or haven't been used in training the machine learning model, then that's certainly a number one thing to look at, first priority in planning.
Yeah, so I would like to just emphasize this is kind of the first thing that if there is one takeaway point, I would say this is the first one.
Yeah.
Do a little bit of a combinatorial analysis and try to identify what has been covered. If you are looking at the training and testing, what combinations have been covered in the training, what is absent in the testing, and then get those combinations of values for testing and use that. And it actually is applicable for regular software testing as well, but in the machine learning model training and testing, we would like to see the use of this particular strategy, is that do an analysis, see what has not been covered in the training, particularly pick those to do the test.
Yeah, I guess as you were talking, going through all the material, is there a way to do some kind of weighting for the factors that you're more or less interested in coverage for? Like if I really care about environment and in my M&S testing, but I have a bunch of other factors, it's computationally prohibitive to do all of them. Is there a way to
prioritize?
Yeah, I mean, there's been some research. In fact, we all just published a couple of different papers looking at, how do you minimize the data used in models in developing the model? So one way is to leave out some factors, and there's approaches to doing that. And another way we've looked at is leaving out some of the rows or some of the input examples, some of the rows of the inputs. Two different ways of doing that, and you can combine them. So yeah, that would probably get at the question you're asking, I think.
There's also variable strength covering arrays.
Yeah.
So you can have higher strength for some of the combinations.
And that's built into ACTS too. You can tell it to do higher strength for certain combinations.
So we are over time. So I'm going to cut us off. I'm going to tell you that we are really interested in the AI T&E domains and problems in your organization, especially those for which you do not have solutions. And we would love to hear about those. And then we have in the slides, there is a request for some participant feedback so that we can kind of improve this short course in the future. So if you could, do that, that would be really helpful. And I just want to thank everyone for coming and sticking with us to the end of the day. I know it was a really long day. We are happy you're here. This is obviously a topic that we all care very, very, very much about. And so we're glad that you let us share it with you. You want to say anything?
Thank you. And it's just to repeat one more time, we love working with people that are doing things in the real world.
Shoot us an email.
Yeah.
I mean, our email.
Let us
should be
know.
there in the
Yeah,
slides
yeah.
at the very
And
beginning, and
and it's also on the website where you were downloading things from.
yeah, it's so yeah, on the website, just shoot us an email if you have a problem, or if nothing else, just it was good. You could improve it this way. There are some formal ways of giving the feedback, but some informal feedbacks are welcome too.
Yeah.
Thank you.